Hi, this is Dr. G, and in this video I will go over the definition of the derivative. Let's go. For the first part of the video, I will illustrate and explain the conceptual basis of the definition of the derivative. In my opinion, if you actually understand it, it actually makes a lot of sense logically. And in the last part of the video, I will go over a few typical examples that you're likely to see that requires you to use the definition of the derivative to solve the question. This equation is the definition of the derivative. First question is, what do we use this equation for? And the answer is differentiation, which is when we're trying to find the derivative function f prime of x from our original function f of x. The definition of the derivative is the first and most mathematically meticulous method of differentiation that you learn when you're taking differential calculus. Because after learning this, you will learn something called derivative rules, which in my opinion are a lot faster and easier to do than the definition of the derivative. Well, you might ask, what is the point of learning the definition of the derivative if derivative rules are so much quicker and easier to use? To that, I might say, although the definition of the derivative might appear as one big equation, it actually conveys a lot of conceptual details within that equation. Let's take a look at the actual definition of the derivative in words. It states that the derivative of a function f of x with respect to x is the function f prime of x. That makes sense. We already know that f prime of x is the derivative of f of x. But how does that sentence translate to this giant equation? This equation says that the f prime of x, or the derivative, is equal to the limit as h approaches to 0 of f of x plus h minus f of x all over h. At first glance, this equation might look really intimidating. It's got limits, it's got a random letter h for some reason that is approaching 0. You have f of x plus h, you got f of x, you got a lot of things going on. However, this actually makes a lot of sense logically if you keep these two things in mind. The first point to keep in mind is that the goal of using this equation is to try to find the derivative, which will help us find the slope at any given point on a function, or alternatively, the slope of a line that is tangent to any point on a function. And second, although it might look like one big expression, there's actually two parts to this expression that, when combined, helps us achieve the goal of finding the slope of our tangent lines. So it's actually better to look at it as two separate components. What we'll do in this video is that we're going to take this definition of the derivative and we'll break it down to two separate components and look at them separately. We'll look at the limit as h approaches to 0, as well as the fraction of f of x plus h minus f of x all over h. We'll first take a look at the right-hand side. Let's pretend that we have a function, f of x, and we have a random point on that function where the x-coordinate is just x because we don't know what it is. You might think that we can label the point as x comma y, which is fair, but instead of labeling it as y, we can instead say x comma f of x, because f of x is the same thing as y. So the goal here, remember, is to try to find the derivative f prime of x, which is going to help us find the slope at that point, or the slope of the tangent line to that point. It's the same thing. But hold on a second. Remember, to find the slope, which is using the slope equation, we need 2 points. Right now, we only have a single point. So we're going to have to put another point on this function, let's say right there. And notice I labeled the x value as x plus h because it's a bit further to the right than my original x value of x. I don't know how much more to the right it is, so I'm going to use the letter h to represent the distance between the 2 points, horizontally speaking. And in that case, I would label the coordinates as x plus h comma f of x plus h. Now that I have 2 points, I can draw a secant line between the 2 points, and using my slope equation, I can plug in the respective y and x coordinates into the slope equation and get something that looks like this. Hold on a second. Doesn't this look familiar? And the answer is yes. It's identical to the right-hand side of our definition of the derivative. So what does the right-hand side of the definition of the derivative really mean? It is just the slope equation for the secant line between our point and another random point. All right, we've established that the right-hand component of our definition of the derivative It's just the equation of the slope of a secant line that we made. But our goal is to find the slope of the tangent line. And as you can see, the secant line that I made isn't very similar at all to the tangent line. And this equation only gives me the slope of the secant line. It doesn't give me the slope of the tangent line, which is what I actually want. Okay, now you might be thinking, well, Dr. G, you picked a pretty crappy point. But what if I picked a better point than the one I did just now? Instead of picking the point that you see here, what if my second point I picked was actually here, a lot closer to my first point? Well, in this case, I can still make a secant line, but do you see how the slope of the secant line now is a lot more similar to the tangent line slope? It's still not the same, but it's closer than earlier. That is very interesting. What did I actually do when I moved the point from there to here? Well, do you agree that the original horizontal distance between my red point and the original green point was h? But because I moved my green point closer to my original red point, the horizontal distance between the 2 points are now closer, meaning my h is getting smaller. So we can conclude that as the value of h gets smaller, the second point moves closer to our original point, which means the slope of the secant line between the 2 points are going to be more and more similar to the slope of the tangent line to the point I care about. Okay, let's go more extreme. Let's move my second point even closer to my first point. As you can see, now the secant line between the 2 points is very similar to the tangent line to my original point. In fact, it can get so similar that the equation for the slope of the secant line can be applied to the tangent line. As the points get closer and closer together, what happens to my h value? My h value is getting smaller and smaller and smaller. To add on to what we said earlier, as the value of h gets infinitely smaller, the 2 points will become infinitely closer to a point where the slope of the secant line is pretty much the same as the slope of the tangent line, which means that the equation to find the slope of the secant line can now be applied both to the secant line, but more importantly, to the slope of the tangent line, which is what we care about. And the idea of h getting smaller is what the limit as h approaches 0 is trying to convey. It's trying to say that we want h to be as small as possible. That's what approaching 0 means. Okay, but then why approach? Why can't h just be 0? Well, if h was 0, then the 2 points technically would be on top of each other, in which case we wouldn't really have 2 points, would we? We would just have 1 point. And if you only have 1 point, then the slope equation wouldn't work because remember, we need 2 points to find the slope. So we have to approach 0. H cannot equal to 0 because if that was the case, we wouldn't have 2 points anymore. We still need the idea of having 2 points, although we want the 2 points to be as close as possible, so the slope of the secant line is as similar to the slope of the tangent line as possible. So we use a term limit because by using limits, we can now theoretically approach 0 without ever reaching 0. Looking at this definition of the derivative now, we can see that the right-hand side simply helps us find the slope between our point and another hypothetical point via the secant line. The left-hand side is going to guarantee us that the 2 points will be as close as possible so that the slope of the secant line we found can be approximated as the slope of the tangent line that we care about. So by first finding the slope of the secant line between 2 points, and then making sure that the points are as close as possible so that the secant line slope is equal to the tangent line, that's how we find the slope of the tangent line to any point, or f prime of x, the derivative. Before we apply the definition of the derivative to answer the questions coming up in a few seconds, I want to quickly go over something that you should always keep in mind when you're solving questions using the definition of the derivative. Using what you learned with limits, you might look at this and say, okay, if my h is approaching 0, then all I have to do is to replace the h's in the equation with 0. But the problem with that is that would end up giving us a 0 in the denominator. And we can't do anything with that because we can never divide anything by 0. Instead, your primary objective when doing questions using the definition of the derivative is to simplify the numerator. In this case, I put some random stuff in the brackets. Just don't worry about that. But the point here is that you should be able to factor out an h on the numerator. And in this case, you're able to cross out the h's, effectively getting rid of the only problem that we have, which is the possibility of a 0 in the denominator. Once we've crossed out the h in the denominator, now we can freely plug in 0 into h anywhere in the equation, and you'll get your answer properly. Let's take a look at this question. It says, find the derivative of the following function using the definition of the derivative. And they've given us a function here. Okay. Notice that they say using the definition of the derivative, which means we're going to have to pull out this big boy and use it to help us find the derivative. All right, so let's focus on the numerator. The numerator has f of x plus h minus f of x. Well, they gave us the function in the question, and that is our f of x, so we're good there. What about f of x plus h? Well, to find that, we just plug in x plus h into the original equation wherever we see an x. We simplify that, and we're going to end up with something that looks like this. All right. Next, we're going to replace the f of x plus h minus f of x with their respective expressions that we simplified. Keep in mind, though, the brackets you see here around the f of x is important because of the subtraction sign. We're going to have to distribute the subtraction sign into the brackets to make sure we make no mistakes. This is a common area where students make mistakes, so please be careful here. Always use brackets. Once we distributed the negative sign into the brackets, we don't need the brackets anymore. We can combine like terms as you see here. We can cross some things out, which is great. And we're going to end up with something that looks like this. Notice that this expression on the numerator, every single term has an h. That's important because only then can we factor out the h as a greatest common factor and cross out the h that we have on the denominator. Now, this expression looks like this, and at this point, we can now confidently replace the h's we see in the expression with 0. And by doing that, you see the limit disappears because we plugged in 0 for h, and we can solve for it, giving us our derivative as 4x minus 8, and that is the final answer to this question. What if they asked us this? Find the slope where x equals 4 for the function. Same function here. Now they want the slope at a point where our x value is 4. What do? Well, the first thing is what we did in the previous question. We have to find the derivative. So we would do exactly what we did in the previous question and end up with f prime of x is equal to 4x minus 8. Once we have the derivative, we're able to plug in our x value into the derivative to figure out what is the slope of the tangent line to that exact point. So by plugging in 4 into my derivative function, you see I get the answer of 8. That means the slope at where my x value is 4 is 8. This is a common question that you're likely to see when you're doing this chapter. Find the equation of the tangent line to x equals 4 for the function this. Again, same function, just to keep things simple. In this case, they want to know what is the equation of a tangent line that touches the point where my x value is 4. Notice the question is asking for the equation of a tangent line. Well, the equation that you need is this one here, which is also known as the point-slope form of a linear function. It's called the point-slope form because you need a point and you need to know the slope, which means when we're answering these type of questions, we're going to have to find the slope as well as finding the point. Well, since we have the x value already, which is 4, we only need the y coordinate. All right, let's get to work. So first things first, how do we find the slope? You might be thinking, hold on a second, didn't we just find the slope in the previous example? And the answer is absolutely. So we would find the derivative. We will plug in x as 4 into the derivative to get the slope of 8. Okay, what about finding a point? When we're trying to find the y coordinate of a point, we don't look at the derivative ever. We always look at the original function. And since we know the x value is 4, we plug in 4 into the original function to get a y coordinate of 17, which means our point has an x coordinate of 4 and a y coordinate of 17. Now we can plot these points and slope into my point-slope form. And by doing that, it will look something like this, which could leave as an answer if they want a point slope form, or you can simplify it and isolate y to get it to look like the slope intercept form. If you like this video, consider subscribing to my YouTube channel and also follow me on my other social media platforms.